Hello and welcome to lesson 7.4 of vectors in three-dimensional space. We're going to talk about creating a three-dimensional coordinate system now using 3-space. So, what we're going to do is notice that the x comes out, the y comes out, and the z goes up. These are our areas where our line are positive, and going out towards the back are where x and y are negative and z is negative downwards. Now, because there is no labels of values on here, you've got to make sure that you put in your values by labeling like so. This coordinate system is often called the right-handed system because it follows the right-handed rule. And we'll talk about that right-handed rule a little bit later. I have also seen that this system is sometimes drawn with a y going out like this, the x coming out like this, and the z going up like this for the positives. Okay. So any general vector A, B, and C in three-dimensional space, or short 3-space, 3D space, can be drawn by finding the coordinates A, 0, 0, B, 0, 0, B, 0, and 0, 0, C. Then drawing a box like so, and coming up with the result. I find this a little bit more difficult to draw, because sometimes I can't draw these three-dimensional boxes very well. So, another option I suggest is actually adding 3 different vectors that you have. So for instance, let's say we have vector A, 0, 0. We add on vector 0, B, 0. And then we add on vector 0, 0, C. If you add up all these 3 vectors, you get your resultant vector of A, B, C in the proper direction and proper length. So let's try this out. Let's draw these vectors on these grids. Don't forget, gotta label these grids. If you do not label the grids, then you can't properly show me where the values are, and therefore we'll lose marks. There are some extra 3D grids found on the D2L Brightspace page that you guys can download and use if you prefer. Okay, so let's draw our first one. So you're going to draw 3, 0, 0 as your first vector coming out from the origin, like so. You're going to draw the vector 0, negative 1, 0 coming from the last vector you just drew, like this. And then you're going to draw the vector 0, 0, 2 coming out from the vector that you just drew. Once you have that, grab your ruler and draw your result. And there's our resultant vector 3, negative 1, and 2. Okay, so I encourage you to pause the video now and try the next one for yourselves. Okay, so now that you tried it out on your own, you should have drew this vector to begin with, followed by this vector here, to get this resultant here. What you'll notice is this vector doesn't actually travel anywhere between for positive values of y or negative values of y. So this is actually said to be in the x-axis or z-axis, or sometimes also in the xz plane. That's how we can describe these kinds of vectors. Okay, so moving right along. So just like any two-dimensional vectors, vectors can be described in algebraic form, so can 3D vectors. So the vector ABC can be written as AI plus BJ plus CK, where I is 1, 0, 0, J is 0, 1, 0, and K is 0, 0, 1. And the magnitude of such vectors can be calculated by just taking a squared plus b squared plus c squared, and all putting it under a square root. All other properties seem to work fine just with three-dimensional vectors, including dot product. So let's take a look at a few examples. So if we have the vector OA and the vector OB, and we want to determine the vector AB, remember to find the vector AB, we can take the vector OB and subtract OA. We proved this recently with Cartesian vectors. So this becomes negative 5, negative 12, and negative 1. As we just saw, to calculate the magnitude of these things, all we have to do is just square each of our values. Add them together and put it under a square root. So this just turns out to be the square root of 170. Okay. As mentioned, dot product remains the same. So let me show you. So OA was our vector 3, 5, 9, and OB was our vector negative 2, negative 7, and positive 8. So 3 times negative 2 is negative 6. We're going to add 5 times negative 7, which is negative 35. And we're going to add 9 times 8, which is the value 72. Together, this all adds up to be 31. Okay. And as well, to find a unit vector in the direction of AB, all we need is the vector AB, which we already found, which is negative 5, negative 7, and, my apologies, it was negative 12, and negative 1. And we also need the magnitude of AB, which we found was square root of 170. So that means our unit vector in the direction of AB is just 1 over the square root of 170 times this vector, negative 5, negative 12, and negative 1. If you wanted 2 unit vectors in the direction parallel to AB, all you have to do is just change this to a plus or minus sign in front. Okay, one last problem. So if U is the vector 5, negative 1, and 4, then determine a vector V that is orthogonal. I'm going to introduce a new word, orthogonal, which means perpendicular to the vector U. Well, if you remember, in order for a vector to be orthogonal or perpendicular, all it has to do is U dot V has to equal 0. So if our vector U is 5, negative 1, and 4. Let's make a vector v. Let's call it x, y, and z. And that has to equal 0. Now please realize it says a vector. That means there are multiple options for vectors that you can use. So if I use my dot product, I get 5x minus 1y plus 4z equals 0. So the best thing to do here is just choose values for x, y, and then maybe solve for z. Or choose values for y and z and solve for x. So let's choose some. So may I suggest us choosing something like, I'm going to choose the value 4 for x, and I'm going to solve for y, but I'm also going to use the value of z to be 5. I get these numbers specifically by reversing the order of these two numbers right here. This will help me solve it a little easier. So this turns out to be 20 minus y plus 20 equals 0. So negative y equals negative 40, or y equals 40. So one possible is the vector 4, 40, and 5. This will make nice numbers and not have to deal with fractions, especially if you use numbers that are already here. Another possible one, all you have to do is just take the values and flip them and make one of the answers 0. So for instance, if I actually flip 4 and 5 here, I've changed one of the values to a negative, so that will get rid of the value. You can use 0 in the other option. And that's how you make perpendicular vectors. We'll talk about orthogonal and perpendicular vectors a little bit more, and thus concludes this lesson.